and welcome. This is Safa. In this video, we'll take a closer look at the core of a sliding mode control, the sliding surface. We'll learn how to define it, what properties it should have, and how to prepare it for implementation in MATLAB. Okay, let's dive in. The sliding surface is a mathematical expression, typically denoted as Sx, that we want the system to reach and stay on. It represents the desired dynamic behavior. Once the system reaches Sx equals 0, it slides along this manifold. Let's consider a simple position tracking problem. Define the tracking error as E equals x minus xd, where x is the current position and xd is the desired trajectory. Now, to define our surface, we can use a first order sliding surface as equal E dot plus lambda e, where lambda is a positive constant that shape the convergence. When s equals 0, we got e dot equal minus lambda e. That implies that the tracking error descends exponentially, which means a stable, predictable behavior that why the surface must be carefully chosen. Okay, now let's switch to MATLAB and simulate the behavior. We'll assume an initial error and see how it evolves over time with a given lambda. Okay. In this script, we define the error et using the solution of e dot equals minus lambda e. As you can see, okay, lambda, initial tracking, time cover, and plotting. The error starts at 5 and converges exponentially to 0. And this shows how effective a well-designed sliding surface can be even before we apply a control input. Okay. So, to summarize, we design a sliding surface using the tracking error and its derivative. And when the system reaches this surface, it behaves in a stable, predictable way. In the next video, we'll design a controller that forces the system to reach this surface and stay there no matter what. Thanks for watching. This is Safa. We're learning together one concept, one line of code at a time.